In this video lecture we will study the effect of harvesting in predator-prey models. Let x of t denote the population of fish, which is the prey in this case, and let y of t denote the population of shark, which is the predator. By construction we are interested in the regions where x and y are non-negative. The equation of motion determining the evolution of x and y is as follows. The x dt is given in terms of combinations of x and x times y, and the y dt is given in terms of combination of y and x times y. As you can see, this is equivalent to the rabbit-fox system. A, b, c and d are for positive constants. So that's the model, and now we introduce a new effect on the model, which is the harvesting. So we will assume we are harvesting using net fishing, in which basically what happens is that the populations both of fish and shark get affected due to the net fishing, because net traps basically all kinds of fish, including shark. So you're gonna get a reduction of both the population of fish and population of shark due to this harvesting. So we model the harvesting with these two terms in blue, which represent the loss, basically using Malthusian law. As I said, represent the loss of both population of fish and population of shark. Notice that this introduces a new constant e, which is assumed to be positive. Notice that in addition we also can impose that a is greater than e, for reasons that will be apparent now. So combining these terms in both terms of right hand sides, we can write like this. The system basically, when we include the harvesting, it's equivalent to a rabbit-fox system, provided we replace the constants that we had for the rabbit-fox system by appropriate new constants. So if we define this new capital A, capital B, capital C, and capital D according to these four formulas, we recover the rabbit-fox system with these new variables. Therefore, all the things we know about the rabbit-fox system also apply to this system. In particular, the existence of critical point, which has interest ecologically. So, this being our system in the boxed equations, let us calculate the position of the critical points. Well, the obvious critical point is when x equals y equals 0. That corresponds to an unstable critical point. And the second critical point is the one that is ecologically very interesting, and it's actually a center which is stable, and it's given by the following formula. So this is the critical point that corresponds to the interesting ecological equilibrium, and it's actually stable, it's a center. And this explains why we require that e is less than a, so that y0 is greater than 0. And of course we still require that e is positive. The same a, b, c and d are positive. Okay, so the first thing to do is to study the averages of the functions x of t and y of t. There will be a very interesting result, but let us first define the average of a quantity. In this case we're going to study the long time average. Consider a function of time t z of t defined for t greater than or equal to 0. Then by definition the average of z denoted by z bar, when an over bar, is equal to the limit when capital T tends to infinity of the ratio of the integral from 0 to t of the function z and the time capital T. This is, of course, the natural definition of an average, and it coincides with the idea of average of a discrete number of quantities. In this case, because z is a continuous function, we produce an integral of this function rather than a sum. So the claim of this part is that the average of x and the average of y can be computed in terms of the positions of the critical points. So simply x bar, the average of the values of x over long times, is equal to c plus e over d, and the average of the values of y over long times is equal to a minus e divided by b. So let us show this claim for the first equation. Let us calculate x bar. We take the second equation of the system of ODEs, namely the equation for dy dt, and solve for x. So we obtain this result, that x of t is 1 over d times a function that depends on y prime over y plus a constant. We can now calculate the integral over time of this function x of t, obtaining this equation. So the integral from 0 to capital T of the function x is equal to this expression in the right hand side. Inside the brackets, the last term is very easy to calculate. It's just the integral of 1 over dt, so the result is capital T. And the first term is the integral from 0 to capital T of y prime over y. And this can also be integrated exactly. So the integral of y prime over y is equal to the log of y, and that gives us this expression. Now we divide by t to define on the left hand side of this equation the average of x, obtaining this preliminary expression, which is valid for all values of capital T greater than 0. Now notice that the logarithm of y is supposed to be bounded. The reason is that the function y, from inspection of the graph of the trajectories, is a bounded function. It is bounded away from 0, so it is positive, and it's also bounded from above. It doesn't grow as much as you want. It has a maximum value, and this is because the trajectories are closed curves. So as capital T goes to infinity, this is what we're going to take now, the limit capital T goes to infinity. As capital T goes to infinity, the function y remains bounded, and therefore the first term in the brackets in the right hand side tends to 0 as capital T goes to infinity. So now taking the limit, we have the limit of the sums. The limit of c plus e, which is a constant, is equal to the same constant, but the limit of the log divided by t is equal to 0. On the other hand, the left hand side of this expression is nothing but the average of x. Therefore we conclude that x bar, or the average of x, is equal to c plus e over d, which is the component of the critical point. In a similar fashion, you can demonstrate that the average of y is equal to a minus e over b. We will leave that as an exercise. So the average populations of fish and shark are given respectively by these two formulae. Now comes the interpretation of this in terms of the harvesting effect. Remember that the harvesting is introduced via the constant E, which is positive constant. The question is, when you introduce harvesting, you introduce this constant E. What is the effect on the population of fish and the population of shark? We can see this by rewriting x bar and y bar, separating the term explicitly, and denoting in blue the effect of harvesting. The conclusion is that when net fishing is introduced, the average population of fish grows and the average population of shark decreases. This is the interesting point, because intuitively one would expect that if you do net fishing, so you are trying to find fish, you expect that the population of fish will be reduced, but the effect is the contrary. The population increases. Of course, the reason of this is that when you do net fishing, you are not only eliminating fish from the system, you are also eliminating shark from the system. And this elimination has a knock-on effect, in the sense that there will be less shark eating the fish. And that's the end of this chapter. Thank you for your attention.